Okay, so we're going to start into electrochemistry, and I'm going to try and tie it back to what we were doing in thermochemistry. So here are two what we call half reactions. When we add them together, we'll make a whole reaction. This is frequently done for oxidation reduction or redox reactions, and so we will be doing some delta G, delta S, delta H kind of stuff with these equations. But first we have to make that into one big equation. Now the biggest problem that we see at first is in an oxidation reduction reaction, one species gives up electrons and another one takes the electrons. So they should be on opposite sides on these half reactions. They're both on the same side. Now, the reason that I gave you them in this format is because these came from a document called Appendix 6, and this is the format that they are in on Appendix 6. So what we need to do first, and on Appendix 6 at the end, clear on the right side, there's a value called E naught. Naught as in N-A-U-G-H-T, that's the little zero, E naught, which is, I believe it stands for EMF, or electromotive force. I believe that's what it is. You could call it energy. You could call it electric charge, or not charge, it's voltage, so it's electric potential. And so there's values for each of these, and they can be either positive or negative, and in this case they're both positive, plus 1.507 volts, and the other one plus 1.358 volts. So what we have to do, we're going to have to flip one of these half reactions to get the electrons on the opposite side. Now, how do we know which one to flip? Well, we can tell that from the E naught values. We want to flip, when we flip it, we're going to change the sign. And when we add the two E naught values together, it needs to end up a positive. The thermodynamic favorability for E naught is E naught greater than 0. So we're going to flip one that when we add them together, they add up to a number greater than 0, a positive number. Since they're both positive, we're going to flip whichever one is smaller. If they were both negative, we would flip whichever one is bigger. Is more negative. And then if they were one positive, one negative, well, that's the easiest. You just flip the negative one. So we're going to have to flip this chlorine one because it's a smaller E naught value than the manganese one. So we'll flip that. I'm going to change the color, make that blue. And then I'm going to dispose of the other one we're no longer using. Okay, so now when we add these together, let's change the color back. 1.507 minus 1.358. I'm getting a value of plus, I'm going to call that E naught cell, plus 0.149 volts. So that's my electricity that will flow if I can separate these two into separate halves. Anyway, so now then we're going to add the two equations together. And we have one more thing we have to do, and we may have talked about this way back in the fall. The electrons not only have to be on opposite sides, but they have to be the same number. We have to have the same number of electrons, or same number of moles of electrons. So with the 5 and the 2, we're going to need to multiply this top one by 2 and this bottom one by 5. Now, unlike other things where we've added equations like this, we are not changing the E naught because, as I understand it, it's an intensive property, which means it doesn't matter how much you've got. It's always the same. So we will not mess with the E naught cell values. So now I'm going to put that arrow right about here. And then everything on the left side goes on the left, everything on the right goes on the right. When I multiply the 5 through, or multiply the 2 through here, I'm going to have, that's going to be a 2, that's going to be a 16, that's going to be a 10, that'll be a 2, that'll be an 8. This will be a 10, a 5, and a 10. And now I'm going to go ahead and cancel my 10 electrons so I don't have them messing up my final equation. So now anything on the left side goes on the left side of the arrow. 2MnO4 minus 16H plus 10Cl minus. And the AQs and all that do matter at this point. And I say that, and I didn't have an AQ up here, and I didn't have a liquid up here. 2Mn2 plus 8 H2O liquid plus 5 Cl2 gas. And now at this point, now we've got the balanced whole reaction, whole equation. And what we want to do now is I want you to find delta H and delta S using what we did before with Appendix 4. The only problem is Appendix 4 does not have this manganese ion in it. So I went ahead, I asked AI, and it told me that this was negative 220.8 for delta H. And for delta S, it is 73.6 negative. And that's joules per mole Kelvin. This is kilojoules per mole. And don't forget, we're going to multiply that by the 2. So if we were doing this in class, we would work out the whole problem like we've been doing, where we calculate delta H. We'll put in all the numbers and products minus reactants. For the sake of this video, I'm going to go ahead and cut to the end and just tell you what they are. Plus 26.4 kilojoules per mole reaction. And the S is 577.8 joules per Kelvin mole reaction, which we'll go ahead and convert that into kilojoules. So now we've got delta H and delta S. We can calculate a delta G, as we've been doing, from this equation. And let's do it at room temperature, or at least at thermodynamic standard temperature, which is 298. And what we get there, I'm getting 172.2 here, and do 26.4, oops, minus 172.2. I'm going to change the color so we can, negative 145.8. So my delta G value, 145.8, tells me that at this temperature, 298, 25 degrees Celsius, this reaction does occur. So we've got two pieces of evidence that it is happening. We got the positive delta E, or E naught value, and we got a negative for delta G. Okay. We're going to find delta G one more way for delta G. I'm going to probably need a new page. All right. On your yellow sheet, you have this equation. Negative delta G equals negative NF E naught. And N is the number of electrons in the equation, or actually number of moles of electrons. So in this case, we had negative, so it's going to be 10 moles of electrons is N. F is Faraday's constant. I believe it is 96,480 coulombs per mole of electrons. Coulomb is a unit of charge, electric charge. And then we need our E naught value, which was plus 0.149 volts. Now, I will tell you, because you haven't had a physics class most likely, volt is joules per coulomb. Joules is energy, coulomb is charge. We got coulombs here. So we need this volts as not volts, but rather joules per coulomb. So now our coulombs are canceling, our moles are canceling. We're going to have an answer in joules. So let's see what we get here. 10 times 96,480 times 0.149. I get 143,000, and it's going to be negative because of that negative. 143,755.2 joules. If I make that kilojoules, negative 143.8 kilojoules. That's our value for delta G, figuring it in this way. So, how does that compare to what we had before? Well, wasn't it 145.8? And this is delta G equals negative NF E naught. Assuming I've got this number right, which I think I do. But anyway, so we're pretty close on both those. Either way, we find out delta G is a negative number and is decently large. So this is really, relatively speaking, gonna happen. And that will wrap up this video for this particular problem. And I will see you when I see you.